You think you know why the sky is blue. Everyone does. You learned it in school. Light scatters. Blue scatters more. Simple. Done. But that explanation is not an explanation. It's just repeating words you memorized. If you actually ask why blue light scatters more, if you dig into what scattering even means, if you question what light is doing when it moves through air, you discover something far stranger than you were ever taught. The sky is not blue because of some simple particle bouncing trick. The sky is blue because of a profound conspiracy between the size of atoms, the nature of electromagnetic fields, and a mathematical accident that makes small things interact violently with short wavelengths. Let me show you what's really happening above your head. Start with the obvious observation. Look up during the day. The sky is blue. Not violet, not green, not red, blue. Why? The standard answer goes like this. Sunlight is white, which means it contains all colors. When that light enters the atmosphere, it hits air molecules. The molecules scatter the light. Blue light has a shorter wavelength than red light, so it scatters more. The scattered blue light reaches your eyes from all directions. That's why the sky looks blue. Fine. But that explanation just moves the mystery. Why does shorter wavelength light scatter more? What does scatter actually mean? And why does wavelength matter at all? Most people stop asking here. They accept the answer. Blue scatters more. That's just how it is. But that's not how it is. There's a reason, a deep reason. And understanding it requires tearing apart what you think you know about light and matter. Let's start with light. What is light? You probably think of light as a ray, a beam, something that travels in straight lines from the sun to your eye. And that's mostly right for everyday purposes, but it's not what light actually is. Light is not a thing traveling. Light is a disturbance in the electromagnetic field. The electromagnetic field fills all of space. It's everywhere, always. And when something disturbs it, the disturbance propagates outward at a fixed speed. That propagation is what we call light. Think of it like a wave on water. The wave is not made of water traveling. The water just moves up and down. The disturbance moves. The wave moves. But the water itself stays roughly in place. Light is similar. The electromagnetic field oscillates. The oscillation propagates. But nothing is actually traveling through space except the pattern of oscillation itself. Now here's the key. That oscillation has a wavelength, the distance between peaks. For visible light, wavelengths range from about 400 nanometers. For violet light to about 700 nanometers for red light. Blue light is around 450 nanometers. That's small, incredibly small. A nanometer is 1/billionth of a meter. You cannot visualize how small that is, but it matters. The wavelength determines how light interacts with matter. Now let's talk about air. What is air? Air is mostly nitrogen and oxygen molecules. Each molecule is a cluster of atoms held together by electromagnetic forces. And each atom is mostly empty space with a tiny nucleus surrounded by electrons. The electrons are not orbiting. They exist as probability clouds. But for our purposes, what matters is this. The electrons respond to electromagnetic fields. When light passes near an atom, the oscillating electromagnetic field pushes and pulls on the electrons. The electrons start to oscillate in response. They're being driven by the field, and here's the critical part. When electrons oscillate, they generate their own electromagnetic fields. They emit light, not new light, the same frequency as the incoming light, but in all directions. This is scattering. The incoming light shakes the electrons. The shaking electrons emit light. That emitted light goes in all directions, not just in the original direction of the incoming beam. So from your perspective, the light has been redirected, scattered. But here's the question. Why does blue light scatter more than red light? The answer is not obvious. It comes from how strongly the electrons respond to the oscillating field. And that depends on wavelength in a very specific way. Imagine you're pushing someone on a swing. If you push at the natural frequency of the swing goes higher and higher. Small pushes build up into large oscillations. That's resonance. But if you push at the wrong frequency, the swing barely moves. Your pushes don't build up. They fight against the natural motion. Atoms are like swings. They have natural frequencies, frequencies at which electrons like to oscillate. For most atoms in air, those natural frequencies are in the ultraviolet range, higher than visible light. So visible light is pushing the electrons at frequencies below their natural resonance. Now here's the mathematical fact. When you drive an oscillator below its resonance frequency, the response depends on how close you are to resonance. The closer you are, the stronger the response. Blue light has a shorter wavelength than red light. Shorter wavelength means higher frequency. Blue light is closer to the ultraviolet resonance than red light is. So blue light drives the electrons more strongly. The electrons oscillate more. They emit more light. Blue scatters more. But there's more. The amount of scattering doesn't just depend on frequency. It depends on frequency to the fourth power. This is Rayleigh scattering. The intensity of scattered light is proportional to 1 over wavelength to the fourth power. Shorter wavelength means much more scattering. Blue light has a wavelength about 1.6 times shorter than red light. 1 over 1.6 to the fourth power is about 6.5. Blue light scatters more than 6 times as strongly as red light. That's why the sky is blue. Not because blue is special. Because blue is closer to the resonance frequency of air molecules, and because the scattering formula has a fourth power dependence on frequency. But now ask a different question. Why is the sky not violet? Violet light has an even shorter wavelength than blue. It should scatter even more, and it does. The sun emits violet light. That violet light scatters strongly in the atmosphere. So why don't you see a violet sky? 2 reasons. First, the sun emits less violet light than blue light. The sun's spectrum peaks in the green-yellow range. There's plenty of blue, but less violet. So even though violet scatters more per photon, there are fewer violet photons to scatter. Second, your eyes are less sensitive to violet. The human eye has 3 types of color receptors: red, green, and blue. The blue receptors respond to short wavelengths, but their sensitivity drops off in the violet range. So even if violet light reaches your eye, you don't perceive it as strongly as blue. Combine these 2 effects, less violet light from the sun, and lower sensitivity to violet in your eyes. The result is that the sky looks blue, not violet. But make no mistake, there is violet light in the sky. You're just not seeing most of it. Now here's something that should bother you. If scattering depends on wavelength to the fourth power, and blue scatters much more than red, why does sunlight look yellow-white instead of red? Shouldn't all the blue have been scattered out? The answer is that the atmosphere is thin. Most sunlight passes straight through without scattering. Only a small fraction gets scattered, so the direct sunlight is slightly depleted in blue, making it look slightly more yellow than it would in space. But it's not dramatically red because the scattering is weak overall. However, at sunset, the situation changes. When the sun is near the horizon, sunlight has to travel through much more atmosphere to reach you. The path length is longer. More air means more scattering. And because blue scatters more than red, the blue light gets scattered away almost completely. What remains is red and orange light. That's why sunsets are red. Not because something special happens at sunset, because the light has to travel through more air, and the air removes the blue. This is the same reason the sun looks yellow during the day and red at sunset. In space, the sun looks white, all wavelengths roughly equal. But on Earth, the blue is scattered out, leaving yellow. At sunset, even more blue and green are scattered out, leaving red. Now let's go deeper. Why does the scattering formula have a fourth power dependence? Why not second power? Why not linear? The answer comes from the physics of oscillating charges. When a charged particle like an electron accelerates, it emits electromagnetic radiation. The amount of radiation depends on the acceleration, and the acceleration of an oscillating charge depends on the square of the frequency. Frequency squared, but the power radiated also depends on the square of the acceleration. So overall, the radiated power depends on frequency to the fourth power. This is not arbitrary. It's a consequence of Maxwell's equations, the equations that describe how electric and magnetic fields interact. The fourth power dependence on frequency is built into the structure of electromagnetism itself. And here's the beautiful part. This same formula explains more than just the blue sky. It explains why clouds are white, why smoke is blue, why the ocean looks different colors at different depths. All the same physics, all Rayleigh scattering or related phenomena. Clouds are white because they're made of water droplets, droplets that are much larger than the wavelength of light. When light hits a large droplet, all wavelengths scatter equally, no wavelength dependence. So all colors scatter together, white light in, white light scattered. That's why clouds are white. Smoke is blue for the opposite reason. Fresh smoke particles are very small, smaller than the wavelength of light, so they scatter like air molecules. Blue scatters more. The smoke looks blue when you view scattered light, but if you look through smoke at a light source, the smoke looks yellowish or brown because the blue has been scattered away, leaving red and yellow. Now, let's consider what happens underwater. Water molecules scatter light just like air molecules, but water is denser than air, more molecules per volume, so scattering is stronger. And water also absorbs light. Red light gets absorbed more than blue light, so as you go deeper, red light disappears first, then yellow, then green. Deep water looks blue because only blue light penetrates that far, But the blue you see underwater is not scattered blue like the sky. It's transmitted blue, the blue that survived absorption. There's a related phenomenon called Raman scattering. In Rayleigh scattering, the scattered light has the same frequency as the incoming light. The electron oscillates at the driving frequency and emits at the same frequency. But in Raman scattering, the interaction with the molecule changes the frequency slightly. The molecule can absorb some energy from the light, making the scattered light slightly redder. Or it can give energy to the light, making it slightly bluer. This is used in spectroscopy to study molecular structure, but the effect is weak. Most scattering is Rayleigh scattering. Now here's something subtle. The scattering we've been discussing assumes the scatterers are much smaller than the wavelength of light. Air molecules are about 0.3 nanometers across. Blue light has a wavelength of 450 nanometers. The molecule is about 1,500 times smaller than the wavelength, so the small particle approximation holds. The molecule sees a nearly uniform field. The field pushes and pulls uniformly across the molecule. That's Rayleigh scattering. But if the scatterer is comparable to or larger than the wavelength, the situation changes. Different parts of the particle see different phases of the wave. The field is not uniform across the particle. Interference effects become important. The scattering pattern becomes more complex. This is called mi-scattering. It applies to fog, mist, and cloud droplets. And in mi-scattering, all wavelengths scatter roughly equally. That's why fog and clouds are white. There's a beautiful continuity here. Tiny particles, Rayleigh scattering, strong wavelength dependence, blue skies, large particles, mi-scattering, no wavelength dependence, white clouds. The transition between them depends on the ratio of particle size to wavelength. Change the size, change the scattering. Now let's think about what this means for other planets. Mars has an atmosphere, mostly carbon dioxide, but very thin, about 1% the pressure of Earth's atmosphere, and the thin atmosphere contains dust, tiny particles of iron oxide, rust. These particles are larger than air molecules but still small enough to scatter light, and because there are so many dust particles, they dominate the scattering. The dust is reddish, so the scattered light is reddish. The Martian sky is not blue, it's butterscotch, pinkish tan, and at sunset on Mars, the sky near the sun turns blue, the opposite of Earth. Why? Because the dust scatters red light. At sunset, light passes through more atmosphere, more dust. The red gets scattered so much that the forward scattered light is depleted in red, leaving blue. It's the reverse of what happens on Earth. Venus has a thick atmosphere, mostly carbon dioxide with clouds of sulfuric acid droplets. The clouds are thick and global. They scatter light strongly, so the surface of Venus is dim, and the scattered light is yellowish. The sulfuric acid clouds are not pure white like water clouds. They have a slight color. So the Venusian sky, when you could see it from the surface, would be a murky yellow-orange. Titan, Saturn's moon, has a thick nitrogen atmosphere like Earth, but it also has haze, organic haze, complex hydrocarbons created by sunlight breaking apart methane. The haze particles are small. They scatter blue light, so Titan's sky is orange because the blue is scattered away. The opposite color scheme from Earth, but the same physics. Now here's a question you might not have considered. Why is space black? Space is mostly empty. No air, no molecules, no scatterers. So light from the sun travels straight from the sun to your eye with nothing to scatter it. You see the sun as a bright point, but you don't see scattered light from other directions. So the rest of the sky is black. The blackness of space is the absence of scattering. This reveals something profound about perception. You don't see light itself. You never do. You only see light when it enters your eye. The sky is blue, not because blue light is floating around up there. The sky is blue because when you look in any direction away from the sun, blue light that was scattered by air molecules enters your eye from that direction. The scattering redirects the light. Without redirection, without scattering, you would see nothing. The sky would be black, even in daylight. This is what astronauts see. Above the atmosphere, looking away from the sun, they see blackness, not because there's no light, but because there's nothing to scatter it into their eyes. Think about what this means. The blue you see is not a property of the sky. It's a property of the interaction between sunlight and air, and your line of sight. Change your viewing angle, and the color changes slightly. Look toward the horizon. You see paler blue because you're looking through more air, and some blue has scattered multiple times. Look straight up at noon. You see deeper blue because you're looking through less air. The color depends on geometry, on path length, on viewing angle. The sky has no single color. It has a distribution of colors that depends on where you look. On Earth, even at night, the sky is not perfectly black. There's always some scattered light, from the moon, from stars, from artificial lights. This is light pollution. Cities glow. The glow scatters in the atmosphere. So the night sky above a city is never truly dark. It's a murky gray-orange. And the stars are washed out. Go to a remote desert or mountaintop, far from cities, and the night sky is much darker. Not black, but dark blue. And you can see thousands of stars, the Milky Way, nebulae, the sky you're supposed to see. Now, let's return to the fundamental question. What is light doing when it scatters? Light is an electromagnetic wave, a propagating disturbance in the electric and magnetic fields. When the wave encounters a charged particle, the oscillating electric field exerts a force on the charge. The charge accelerates, and an accelerating charge emits electromagnetic radiation. This emitted radiation is the scattered light. But here's the deeper point. The original wave and the scattered wave are both disturbances in the same electromagnetic field. They're not separate entities. They interfere with each other. They add, constructively in some directions, destructively in others. The result is a modified field. The original wave continues forward, slightly weakened, and new waves propagate in other directions, the scattered waves. This interference is why scattering has the pattern it does. Rayleigh scattering is strongest perpendicular to the direction of the incoming light, weakest along the direction of the incoming light. That's not obvious. It comes from the math of oscillating electric dipoles. An accelerating charge in one direction radiates strongest perpendicular to that direction. So if the incoming light is traveling horizontally, the scattered light is strongest in the vertical direction. That's why the sky is brightest overhead when the sun is near the horizon. Now here's something that connects to a much bigger picture. The fact that scattering depends on wavelength is not just a curiosity. It's a manifestation of a deep principle. Scale matters. Physical processes depend on the ratio of sizes. The size of the scatterer compared to the wavelength of the wave. When the scatterer is much smaller than the wavelength, you get Rayleigh scattering. When it's comparable, you get Mie scattering. When it's much larger, you get geometric optics, reflection, refraction, shadows. This is a universal pattern in physics. Scale determines behavior. Quantum mechanics matters at atomic scales. Classical mechanics matters at human scales. General relativity matters at cosmic scales. The wavelength of light sets a scale. Anything smaller than the wavelength behaves one way. Anything larger behaves differently. The blue sky is a reminder that scale is fundamental. And here's the final twist. The blue sky is an accident. Not in the sense that it's random, but in the sense that it depends on specific values. The resonance frequency of air molecules, the spectrum of the sun, the sensitivity of human eyes. Change any of these, and the sky would be a different color. If air molecules had resonance in the visible range, the sky might be dark, all the light absorbed. If the sun emitted more ultraviolet, the sky might be violet. If human eyes were sensitive to infrared, the sky might look completely different. The blue sky is a conspiracy of constants. Atomic sizes, binding energies, stellar temperatures, photoreceptor proteins, all tuned in such a way that scattered sunlight appears blue to human eyes. It's not designed, it's not inevitable, it's contingent, the result of how chemistry and physics happen to work out in this particular universe. So, why is the sky blue? Not because blue is special, because air molecules are much smaller than visible wavelengths, because their resonance is in the ultraviolet, because scattering strength depends on frequency to the fourth power, because the sun emits more blue than violet, because your eyes are more sensitive to blue than violet. Every piece matters. Remove one, and the sky changes color. The standard explanation, blue scatters more, is not wrong. It's incomplete. It's a label. The real explanation is a cascade of electromagnetic physics, atomic structure, and quantum mechanics. Light is a wave in a field. Atoms are oscillators. Wavelength sets the scale. Resonance determines response. Acceleration produces radiation. And the combination of all these factors produces the color you see when you look up. Reality is not obligated to make sense to your intuition. It is only obligated to be consistent. And the sky is blue because the universe is consistent.